This is the Su-27, a Mach 2 Soviet interceptor codenamed Flanker. Its agility and power are an eloquent testimony to Soviet aeronautical design. The proposition is that the Flanker's manufacturer, the Sukhoi Design Bureau, joined forces with the American aircraft company Gulfstream to produce a 12-seat supersonic business jet. Because of its small size, such a plane may be able to travel supersonically over land at speeds in excess of Mach 1. The $50 million price tag for this aircraft may seem a little steep, but Gulfstream is confident that around 100 potential customers feel that much need for speed. And no one denies that speed is attractive. In a civil transport world which anticipates a twofold increase in air travel by the end of the decade, especially across the Pacific, Boeing is still working on perfecting a 300-seat, 5,000 miles, second-generation supersonic aircraft. They believe there may be a market for over 1,000 of them. And that old supersonic partnership, French and British industry, is also working on a second-generation Concorde. While in Germany, the Mach 5 Zanger designs are receiving serious consideration. But in 1989, 20 years after the realization of John Kennedy's dream of putting a man on the moon, another presidential challenge was laid before the world.
So yes, this nation remains fully committed to America's space program. We're going forward with our shuttle flights. We're going forward to build our space station. And we're going forward with research on a new Orient Express that could, by the end of the next decade, take off from Dulles Airport, accelerate up to 25 times the speed of sound, attaining low Earth orbit, or flying to Tokyo within 2 hours.
The public was enchanted by the prospect of a 2-hour trip from Washington to Tokyo. But whether such a technological leap is possible by the end of the decade, or ever for that matter, is a big unknown. Still, a forerunner of President Reagan's Orient Express is already in the works. The X-30, or National Aerospace Plane. Like all X-planes, this one is designed to test a range of technologies, including new materials and propulsion systems. Its ultimate goal is to develop a new kind of space vehicle, one that would replace the existing mainstay of our space program, the shuttle. On takeoff, the shuttle must lift not only its own weight, but the weight of its fuel as well. Within minutes, that fuel will have been burned, and it will be time to jettison the 2 auxiliary booster rockets and then the spent fuel tank. Once in orbit, the shuttle's 17,000 mile/hour speed alone keeps it up, weightless. But as it re-enters the Earth's atmosphere, unpowered, it briefly becomes the world's fastest glider. An impressive achievement, the X-30 designers all agree. But wouldn't it be better if the next space vehicle didn't have to throw away so much expensive equipment on its journey into space? If it could be, to use the jargon, a single stage-to-orbit vehicle.
With a single stage-to-orbit vehicle, we can fly directly from our point of departure, an ordinary runway, fly straight into orbit without losing or having to throw away any parts of the airplane. And from the perspective of operating costs, simplicity, lower complexity, it has a lot of advantage.
But while the advantages are clear, the challenge of flying directly into space is, to say the least, daunting.
One of the advantages of staying in the atmosphere is that you can get the oxygen from the air to feed the engines. That means that you don't have to carry that oxygen with you. Now, what goes along with that is the fact that the airplane has to operate at very high speeds in the atmosphere, and as a consequence sees high temperatures, much, much higher than say, a space shuttle or a typical expendable rocket would see.
Atmospheric heating had been a focus of research since the X-15 program and was a crucial factor in the design of new materials for the shuttle. But the X-30 will experience much higher temperatures than the shuttle, and for much longer periods of time. So the materials from which it will be constructed are going to have to be revolutionary. In some parts of the X-30 structure, liquid hydrogen at minus 300 degrees centigrade will be used to cool the inside of the aircraft's skin. But the outside of that panel may be at 3,000 degrees centigrade. These materials must not only be able to survive appalling thermal stress, they must be both very light and very strong. To meet these needs, new titanium and ceramic structures are being developed and new test methods devised to explore their capabilities. This is the 40-megawatt argon plasma wind tunnel, in which the combined effects of high temperatures and aerodynamic loads on some of the more vital engine parts can be analyzed together. But a further problem plagues the X-30 designers. Exotic as these tests may seem, it's almost impossible to actually duplicate the flight conditions which the X-30 or its engines will experience as it hurtles through the atmosphere at Mach 25. None of the wind tunnels currently available to scientists can produce such air speeds for anything more than a few milliseconds, and sustained high-speed facilities beyond Mach 8 simply don't exist. To solve such problems, supercomputers are used to create imaginary wind tunnels, numerical laboratories in which data from a host of separate flash tunnel tests is integrated into an overall picture of the pressures and temperatures the X-30 and its components will experience. Supporters of the National Aerospace Plane believe that within another year or two, both the material scientists and the aerospace engineers will be confident enough in their predictions for a full-scale aircraft to be constructed. By 1995, the X-30 could make its first flight, and these computer simulations may become a reality. Utilizing data retrieved from astronaut Joe Engle's countless simulator flights, in 1997, the space plane may be flying at Mach 25 to the edge of space and back. If all goes well, by the dawn of the new millennium, the X-30 will be routinely flying into orbit. And then someday, far into the next century, the descendant of this shuttle replacement might become the passenger-carrying Orient Express of President Reagan's imagination. But it takes more than a presidential decree to ensure the success of a project that is this challenging and which will take so long to achieve. It will take a lot of money and a lot of perseverance, and it will also, say the X-30 scientists, take vision.
When we crossed the continent at the turn of the 19th century, we were going from St. Joseph, Missouri to Sacramento in an expendable vehicle, just like we're going to orbit now, called a Conestoga wagon. Very few ever came back. If they did, they needed a great deal of rehab and maintenance. It did allow colonists to go out, but it did not allow for two-way trade. The two-way trade were the ships around the Horn. And it wasn't until the visionaries, the industries, whatever you, robber barons, whatever you want to call them, the railroad people said, we need the government's cooperation, which they did by giving them land grants, and they proceeded to put in a pathway to the west, which was less dependent upon weather, schedulable, lower cost, non-expendable, and more importantly, the trade went both ways. Passengers could go one way, products, gold, cattle could all come back to the east. If we lose the X-30, we lose that vision of a railway to space, and we're going to be stuck with Conestoga wagons.
If the X-30 does take to the skies, meeting the enormous technical challenge of flying up to orbit and flying back, then the prospect of that railroad to space will be a major step closer to being a reality. A reality that is the natural successor to those wood and linen contraptions of over 90 years ago, and the direct descendant of those first true space planes, the X-planes, the fastest planes in the sky.
We can say that the X-30 is the X-15 of this era, as the X-15 gave us a great deal of understanding about the problems and situations of high-speed flight. The X-30 points the same way toward the future.